is on Trigonometry Part 2, Chapter S. We'll define an oblique triangle. An oblique triangle is a triangle where none of the angles equal 90 degrees. To solve an oblique triangle is to determine all of the components of the triangle which are not given. There are three components to a triangle, and they are 3 sides and 3 angles. The topic I'm going to deal with now is referred to as the Sine Law. This involves an oblique triangle given 2 angle measurements and 1 side. This amount of information about a triangle produces a unique solution. The Sine Law states that the length of the sides of the triangle are proportional to the sines, the trig function sines, of their corresponding angles. In symbols as proportions, we have A over sine A equals B over sine B equals C over sine C. The letters along the bottom are capital, representing the angles. Letters across the top are small letters representing sides. There are 6 possible combinations of ratios. Therefore, we have 3 proportions. These 2 may be combined to get 1 proportion. These 2 may be combined to get another proportion. And these 2 may be combined to get a 3rd proportion. Selecting one pair of ratios for a given proportion. If you know 3 parts of the proportion, the 4th proportional can be solved for. And here is the proof for those proportions. We will draw two triangles. One will be acute angled, and an obtuse angled triangle. So we will construct we'll refer to this as triangle A, B, C, and hence this side is small a, this side is small b, and this side is small c. Similarly, A, B, C, and small a is there, small b is there, and small c is there. The first step is to drop perpendiculars from vertex A to base BC or BC produced. And call this perpendicular H for the height, let's say, of the triangle. H, 90 degrees. We will have to produce BC along a straight line and drop the perpendicular there. That's 90 degrees, and that's H. It follows from this diagram here that sine B is equal to opposite over the hypotenuse in this right-angled triangle. The sine of B is the opposite over the hypotenuse, and so sine B is equal to H over C. In this particular diagram, the sine of 180 degrees minus B is equal to H over C. If this is the angle B, and it is of the triangle, and this is a straight line, then the angle on the other side of it, the exterior angle, is 180 degrees minus. And here then we have a right-angled triangle involving H, the length AB, and this line produced. So looking at this exterior angle 180 degrees minus B, the sine of it is the opposite H over the hypotenuse, which is the length C. That's the hypotenuse of this exterior right-angled triangle. So that's a true statement. If you solve for H here, H is equal to C multiplied by the sine of B. If you do the same sort of thing with H over here, H is equal to C times the sine of 180 degrees minus B. But recall from an earlier tape, the trig sine of a second quadrant angle is equal to the sine of its related angle, the related acute angle. And in this case, of course, the related acute angle is B. So the sine of 180 degrees minus B is equal to the sine of B. Yield the same amount. Again, the sine of C in this diagram, using this other right-angled triangle, is equal to H over B. And consequently, we can say, by multiplying through by B, that H is equal to B sine C. On this side, the sine of C, here is the large right-angled triangle involving the angle C. The sine of C, this angle, is the opposite side H over B. The sine of C is equal to H over B, and consequently, multiplying through by B, for this diagram, H is equal to B, the sine C. Both results here and here refer to the same height, H, of the triangle. H is equal to C sine B, and H is equal to B sine C. The same thing is occurring under the obtuse angled triangle solution. But these are the two I want to concentrate on, and so I will only color those two in. It follows then, since both the right-hand side of the equal sign equals to the same quantity H on the left, that C sine B must equal B sine C. Writing this equation as a proportion, it is B over sine B equals C over the sine of C. This is one of the proportions out of three that I gave you earlier. If I take some other perpendicular, I will involve the third ratio in this law. And so the conclusion is that B over sine B is equal to C over sine C, and also equal to A over the sine of A. That proves the law. For example, solve the triangle given that angle A is 60 degrees, angle B is 55 degrees, and that the side A is equal to 40 units. We draw a triangle, and we can introduce the information that angle A is 60 degrees, B is 55 degrees, and the side A, which is opposite capital A, is 40. The angle C can easily be found by subtracting the sum of 60 and 55 from 180 degrees, so the third angle is very quickly found. We'll write that angle C is equal to 180 minus 60 degrees plus 55 degrees. Now, taking a proportion out of the sine law of three ratios that involves three of the components known, we can use small a, which is 40, and consequently we'll have to use the sine of capital A, together with either the angle B to find small b, or the angle C to find small c. It doesn't make any difference. You will have to use both eventually anyway. So we can write that small a over the sine of A is equal to small b over the sine of B, and make our substitutions. 40 for that, The sine of A is the sine of 60 degrees, followed by B, which we don't know the value of, and finally the sine of 55. Use your calculator to determine the trig functions of those angles. And so we have 40 divided by, now sine of 60 is equal to 0.866 approximately, is equal to B over the sine of 55, which is 0.819 approximately. B is therefore equal to 40 divided by this amount multiplied by 0.819. Your calculator, the result is 37.8 approximately. So we have then the value of B established. We have one more component to find, and that is C. We begin again and write A over sine A equals C over sine C. Filling in the values that we know, 40 over sine 60 degrees is equal to C, which is not known, over the sine of 65 degrees. Using the calculator again, we can quickly fill in these amounts. Since we know them, we simply have to work out, using the calculator, the sine of 65, and that's equal to approximately 0.906. C is therefore equal to the product of 40 and 0.906 divided by 0.866. And the answer is 41.86 approximately. And therefore, all of the components of the triangle are known, and hence the triangle is solved. In another example, solve the triangle given angle A equals 10 degrees, angle B is equal to 45 degrees, and the length B, the side, is 75 units. Draw a diagram of the problem first. A, B, C, and A is 10 degrees, B is 45 degrees, and we know that B, small b, is 75. We can find angle C very quickly here by taking 180 degrees minus 10 degrees plus 45 degrees. This is 180 degrees minus 55 degrees, and that amounts to 125 degrees. So actually angle C is an obtuse angle. If it helps, you can redraw this, but it isn't necessary. We have then one of the components already, simply by using the property regarding the sum of the angles of a triangle. Use the components now that fit the sine law proportions. We have B, small b, the opposite side of capital B, given, so we'll have to use that ratio, B over sine B. And what we use for the other ratio won't make any difference. We'll have to do both anyway, so we'll take A over sine A. B is the quantity 75. Capital B, the angle, is equal to 45 degrees. That'll equal A, a quantity that is not known, divided by the sine of A, and capital A is 10 degrees. That'll be the sine of 10 degrees. Substituting for those trig expression, their functional values, the sine of 45 is approximately equal to 0.707, and the sine of 10 degrees is equal to 0.174 approximately. A can now be found by multiplying 75 by 0.174 and dividing by 0.707. And we have 18.42 approximately. Continuing, we'll use B over sine B again, but this time we'll use C over sine of C. 75 over 0.707 we have already established. C is not known, and we write now the sine of angle C, which is 125 degrees. Now, as far as the sine of 125 degrees is concerned, that is the second quadrant angle, and its algebraic sign is positive. We can replace the 125 by its related acute angle in the first quadrant, but that isn't necessary. Your calculator will handle the obtuse angle anyways, but we can have the sine of 55 degrees here if we wanted to. Let's use the sine of 125. The sine of 125 is equal to 0.819 approximately. So what we have here is 75 over 0.707 is approximately equal to C over 0.819. Continuing over here, C is equal to 0.819 times 75. That is approximately equal to 86.90. So all of the remaining components have been solved, and therefore the triangle has been solved. There is C, here is A, and we solved for angle C early. The second type of problem involves a triangle given two sides and an angle that's not contained by the two sides. Under those circumstances, it is possible to have no solution, one solution, or two solutions. Some textbooks refer to this as the ambiguous case, but really there's nothing ambiguous about it. Number of solutions to such a problem will depend on the size of the measurements given for the given components. Let's begin with angle B equal to 35 degrees and a side C equal to 20. Side C, small c, equals 20 units. Let's draw part of this figure. We will make this B and this length C. And so somewhere here is the angle C and up there is where angle A is. This is 35 degrees. Now, if we're given two sides and an angle not contained by the two sides, the other side given must be side B. Because if A were given, then 35 degrees would be made up by the arms of the sides C and A, and it is a contained angle. So the second side must not contain the angle with the first side. It must therefore be the side B that's given. Obviously, we don't have angle A a fixed size, so the size of A is flexible. If the length of side B is given that's less than the perpendicular distance, here is the perpendicular distance. If that length given is less than that amount, in green, there is no solution. In other words, the perpendicular, let's call it the height h, is equal to 20 sine 35 degrees. The vertical height from angle A is therefore equal to approximately 11.472 units. So if B is less than that amount, that is the opposite side to the angle given, 35 degrees. So if B is less than C sine B, that's 20 times the sine of 35 degrees. Then there is no triangle and there is no solution. That it takes care of one possibility. I'll continue with what I have on the board here, but now I will change some of it. If the length of B is equal to h, if the side B is given and it equals to the